Our next speaker is Ken Tate. Ken is a cooperative extension specialist in the Department of Plant Sciences. Ken has done an awful lot of work up here at Sierra Field Station for a number of years, despite his youthful appearance.
Yeah, getting less youthful every day these days, guys.
And what he's going to talk to you about is water quality and conservation, and we're going to talk a little bit more about it when we get out in the field as well.
Okay.
This is going to be a big issue for this year, as you well know.
Okay, can you guys all hear me? All right. Okay. Right now we're in this transitory period where a lot of cattle are starting to come off of rangelands as they dry up, and we're moving on to irrigated pasture. And as already indicated, we have about 4,000 plus acres of annual rangeland here, and about 150 acres of irrigated pasture. And this mixture of forage types is really important to most livestock production. Livestock producers around here to really meet that forage demand that those livestock have year-round. So in the winter, we're most interested in water quality and rain coming off of annual rangelands when we have rainfall and natural runoff. This year we didn't have a whole lot of rainfall, so we didn't have a whole lot of runoff. During the summer, we're mainly interested in these irrigated pastures and understanding the tailwater that's coming off of these fields as a result of irrigation. Most of the fields that we have are flood irrigated, which is relatively common. Some folks have sprinkler, but the flood irrigated systems can generate a lot of tailwater if we're not careful, a lot of water that comes off. And most of it goes into these natural small ephemeral channels that drain most of this landscape. And so we have this facility here, which is just a natural laboratory for us that allows us to really examine how management of livestock, of irrigation, we use prescribed fire, how these things over the long term will affect hydrology, basically how these watersheds, how these pastures yield water, and then the quality of water that's coming off of them, how much erosion is occurring, how much sediment is there, what's the bacterial load, say E. coli or some pathogen that we might be concerned about if somebody's drinking the water downstream. What's the level of nutrients that are in there? Because if we get too many nutrients in the stream, we can essentially over-fertilize it, and it leads to eutrophication, excessive growth of in-stream plants, which can utilize oxygen. If you reduce the oxygen in the stream, then you don't have enough oxygen available for some of the aquatic species, like salmonids, salmon, and others. And so all these things we're able to look at kind of simultaneously here at the field station, and as close to the management scale as we can get. And so I'm going to talk a bit about rangelands to begin with, and when I'm talking about rangelands, I'll use the term loosely, but we're talking pretty much specifically about the oak woodland in most of these data that I'm going to show you. And we graze these with it's a cow-calf herd, pretty typical production herd, and most of our rangelands here we're grazing during the wet season. There is some dormant season grazing, but generally with cull cows and that type of thing. And so what do we see in terms of hydrology? How does this very typical landscape yield water? Well, we've got data from the Schubert watershed, which is just about a half mile from here, just over that way, where since 1981 through this data is 81 through 97. That's when we published the first paper on it. We've got an additional now almost 10 years of data. So we've got this almost approaching 30-year data set, looking at every year how much rainfall occurs. And so we get on average, we've recorded about 28 inches of precip at this site on that watershed. That watershed's about 300 acres in size. Look at the standard deviation. That's a measure of variation around that mean. So we can look at the average, but in a landscape like this, we know that the variation is great. And when the standard deviation is that big, that's telling us we've got some pretty low years in that record and some pretty high years in that record. So the average can be a bit deceiving. This looks to be one of those low years. Thinking about, well, if you get on average 28 inches of rain, about half of it, 48%, runs off as stream flow. And so we yield, we call it effective rainfall, we yield about half the water that comes onto this watershed runs off. That's quite variable too, though, driven by precip. Some years, depending on the rain, we can get rain slowly every couple weeks, and we can get quite a lot of rain under those conditions, grow really good forage, and not generate very much runoff at all, because there's time in between those precipitation events for the forage to use that water and for it to evaporate. Or if we get a lot of rain in a row, like we tend to get sometimes over Christmas and in February, we can have a whole lot of runoff. And it's under those conditions that we see most of the pollutants leaving this watershed. About half the water is used by plants, as Roger indicated, basically to support growth and support livestock production and wildlife habitat and that type of thing. So what kind of data does it take to generate these kinds of results? And so thinking about these streams, those of you that live in this landscape, this is a stream draining a 300-acre watershed, so it's relatively small. It's got a few springs on it, so it runs year-round. But this was a series of storms that occurred in December of 2001. And basically along here is from midnight to midnight to midnight. So this is a day. And so you guys know these streams are really flashy up here. And we get a storm coming in. The blue line is the depth, basically the amount of water, cubic feet per second. So it goes from almost no flow over a course of just 12 hours, comes up, peaks, drops way back down over the course of a day. Along comes another storm, peaks and goes up. And so we measure stream flow every 15 minutes so we can get these numbers of how much is coming on, how much is going off. And then we take a water quality sample roughly every hour, every couple hours during every storm. So these dots are the values for fecal coliform, which is a bacteria, and E. coli, which is also a bacteria. That's the concentration, that's the number, colony forming units, per 100 ml of water, basically per glass. And so we're able to, by capturing this data very frequently, see kind of the natural flushing, the natural leaching, if you will, of these kinds of pollutants off of these lands. And this is really important because a lot of folks are interested in water quality. There's a lot of concern about water quality. And we tend to make a lot of decisions on water quality monitoring, right? Take some samples, you're over standard, so you've got to change your management. Or you're under standard, so you're okay. That's how we manage water quality from a regulatory perspective. One of the challenges is, over the course of a day or so, you can go from 1,000 or less, just a few hours, you're up to 4,000. Then you're up to 8,000, and then you're back down. And so depending on when you show up to take a water quality sample, it's going to give you a very different story. And so thinking about how we interpret water quality data and how we set water quality standards, we've really been able to have some influence with this kind of data. One thing, just the water quality standard for E. coli and for fecal coliforms is about 200. And so you know right off that on these kinds of grazed watersheds, which this one is, we're certainly exceeding that standard pretty heavily. And we find this consistently. Then you've got to look over the course of the season to really get a picture of what's going on. How is management affecting water quality? So the kinds of data that I'm going to show you in just a bit are based upon averages of this is a year of data, basically from November all the way through the beginning of the wet season through the beginning of the next wet season. Again, looking at E. coli, fecal coliforms, and all these little storm events that occurred during this water year. And so then looking collectively at all of these samples, we're able to generate some estimates of the quality of water coming from watersheds that have different levels of grazing or different types of watershed management. And so we have show you then, so this is these values are the means of basically 3 watersheds worth of data like this. We have a watershed that's not been grazed, in this case for about close to 10 years, compared to a watershed that's got moderate grazing, which is grazed much like Roger indicated, where you're really trying to optimize forage production, optimize livestock performance, and leave enough cover, enough plant material so that you do get regrowth. These are recommended conditions. Heavy grazing, where you're basically always down in that low growth curve, almost set stocking. And then this tells you, put it into context, these are the water quality standards for sediment, which is a metric for erosion. None of us want erosion, right? We don't want to wash soil off of our land, so we want to minimize that. We also don't want to fill in reservoirs, and we don't want to clog irrigation channels, and we don't want to clog spawning gravels for salmon. So we want to keep those to a minimum. Nitrate's something we want to keep low. Unfortunately, there's not a water quality standard for sediment, so it's just a relative comparison. Nitrate, there are 2 standards that are out there. There's a standard of 10, not to exceed 10. That's for drinking water safety. So if nitrates get too high in water, there's a blue baby syndrome. There can be a lot of problems if that number gets above 10. And then for the purposes of trying to make sure we don't over-fertilize, over-nutrify downstream water bodies, a suggested level of about 1, not to be exceeded. For E. coli, EPA right now is recommending a standard of 126. And so as we go sediment, if we go from no grazing through heavy grazing, we can see that we do increase over time. With it grazing intensity, we will increase the amount of sediment coming off. But relatively speaking, these are very low numbers. Even though with heavy grazing we see more, the soils are relatively resistant to erosion, and Toby will talk a bit about that in the field as we look at some soil pits and why these soils can hold together fairly well. You go over on the coast, and it's a totally different story. You start grazing really heavily, and you start seeing very significant increases in sediment just because of the different soil type. Nitrate, we see an increase in nitrate, but we stay under the recommended limit in most cases, so I don't think nitrate's a major issue for us in these watersheds, although there is some natural leaching of nitrate. Where we chronically see issues is with this indicator bacteria, E. coli. An important thing to point out, and this is something we're able to help inform regulators as well as agency folks, is even with no grazing, the natural levels, the natural background levels of this indicator bacteria exceed the water quality standard. So the water quality standard is not really achievable. The ultimate thing a manager can do from a livestock perspective is if you remove cows, right? That's about the best you can do. And if you do that, which means you can't probably pay the taxes on the land, you're still not going to achieve that standard. And we consistently show that. However, and at moderate grazing, we consistently show that at moderate grazing, we're not really increasing, on rangelands, increasing it that much above background levels. So moderate grazing has potentially some traction. When we start going to heavy grazing and just more animals, more butts out there, we eventually start picking up these indicator bacteria in the water. And so there's 1 million to 10 million E. coli per gram of bovine feces, of cow feces, 1 million per gram. So you think about how much a cow defecates a day, that's about 7 trillion E. coli a day per cow. And so I'm amazed we see so little. And thinking about why we do see so little coming off of these watersheds is, if you go out, if you look at a moderately grazed rangeland, which has function in terms of the plant community, it also has some good function in terms of the soil and the capacity of the soil to infiltrate water. And so we're finding on moderately grazed rangelands that fecal pad hits the ground, it's got, 500 billion E. coli in it, 20, 30 rainstorm events come, and we monitor downslope, either 1 foot or 1 yard, and capture all the runoff that's coming off of that hill slope below that fecal pad. Over the course of a year, we're finding greater than 90% of the E. coli is either trapped in the fecal pad or within 1 foot. So there's immense trapping right there. So, having cattle in the landscape is not in itself a risk. It's where they're defecating relative to runoff, relative to the stream. And then for each additional yard between that fecal pad and, say, the creek, we get an additional 70 to 99.9% reduction. So maintaining the plant community, maintaining the soil's capacity to filter is really the best management practice that we can employ. The other thing is, anything we can do to distribute these fecal pads away from the creek is a good thing. We find that 50% of the manure that beef cattle deposit on rangelands in California are associated with some kind of attractant, the water tank, the salt lake. 50% of the manure is in the area where they loaf or spend a lot of time. So you for sure don't want to encourage that behavior down by the stream. This is not where you want to put your salt lake. Hopefully this isn't the only drinking water that you have in the field, because those are things you can do to try and pull this away and allow that land to filter those constituents. Thinking about irrigated pasture. So the way we graze irrigated pasture compared to rangeland, there's about 90% higher stocking rate. There's about 10 times more animals per acre for the year on irrigated pasture here than we have on annual rangeland. So very productive, very valuable. That's why we irrigate them. As a result, though, relative to rangelands, if we look at, this is from about 1,000 data points collected off of pastures at this facility, grazed as they graze. E. coli, we see on average across these 1,000 samples about 10,000 CFU. Remember, the standard is 126. On rangeland, at the heaviest grazing, we saw about 1,200. So that 90% increase in stockings leading to about a 90% increase in E. coli that we're finding in tailwater from irrigated pasture. Maximums are huge. Nitrates, not so bad, but we start, on average, we're okay, but we do have some exceedances of that 1 value that we're trying to stay under. And you see we get also about an order of magnitude more, 90% more sediment. More cattle, more hooves, more butts, more fecal material, and greater runoff because we're irrigating these fields. So we're certainly not going to not graze irrigated pasture, right? And we're going to try and optimize our use of forage because we're putting money into it. So then what are some alternatives that we can do with grazing management and the capacity to perhaps filter that water coming off those fields? And so right out here, just outside this door, we had an opportunity where we have a small wetland. I think Art burned it a while back, maybe a couple weeks ago, because we had some blackberries starting to grow in it. So putting up a wetland is a great thing to do, but you still have to manage the vegetation that's within it. Otherwise, in this landscape, it will become a blackberry patch. And we want it to have a different plant community composition than that. We want it to be able to filter water. So we have a wetland. And whenever these pastures, irrigated pastures, are irrigated, their tailwater comes into an ephemeral channel that only runs water when we're irrigating with the tailwater, runs into that wetland and runs out of it. So we could sample above the wetland and below it and figure out, one, well, what's coming off these fields, what's going into the wetland, and then what's coming out of the wetland. And so we wanted to look at the same time at, well, the wetland potentially can filter this water and reduce, say, E. coli levels. But we also want to look at, well, what can we do on the pasture? Maybe if we don't graze while we're irrigating. Maybe if we rotate those cows out based on plant foraged conditions ahead of irrigation a couple days, let those fecal pats dry out, let them crust, let some mortality occur, let some of the E. coli in them die, let some of the nutrients in them become decomposed, maybe lost. How would that work? And then, can we just reduce irrigation runoff rate? You know, if this pollutants are being transported off of these fields in our irrigation tailwater, which we have control over, right? We can control the level of water that we put on the field, unlike rangelands where we get what we get with the rainfall. So can we manage irrigation to reduce the amount of runoff and thus the amount of transport? And can these three things together give us an added benefit of scrubbing, if you will, the water off of these irrigated pastures? And so we had two wetlands that we rolled in the study, and one was somewhat channelized. The other had, so the water came into the wetland and it stayed in a little bit of a channel. In the other case, it came into the wetland and it was spread out, interfaced with all the wetland, and flowed through it pretty evenly and pretty slowly. We looked at 3 different application rates across about 16 trials on each one, so we could get low to high runoff. And then we basically changed the timing of grazing before we irrigated as well. And so the functioning wetland, the water spread out, went through it, and took about 2 hours for the water to pass through that wetland. This wetland, none of the guys, they've all conveniently left. Somebody with a backhoe obviously tried to drain that wetland. Nobody around here will admit to it. Those guys are probably retired, I'm sure. And so what's happened as a result of that channelization, about 70% of the water that enters the wetland stays in this channel. About 30% of it actually goes into the wetland. So different hydrology. And so looking at the results of what we found over all this, just looking at what's the effect of the wetland, how much reduction do we get? So if you look at this graph, we've got E. coli, sediment, nitrate, total nitrogen, total phosphorus, phosphate, percent reduction. If it's positive, that means that was the percent of what came into the wetland stayed in the wetland. If it's negative, that means there was actually more coming out of the wetland than going into the wetland. The wetland was a source here, was a sink here. The green is the functioning wetland. The kind of teal, I guess, is the channelized wetland. And what we found was that the functioning wetland, for all of these constituents, you know, on average, greater than 50% reduction. So it was very effective at trapping these pollutants. Very effective for sediment, which we would expect. We found that, however, the channelized wetland was actually a source for sediment. And that's because that channel that's in there is still eroding. And so putting water through that channel is still generating a little bit of erosion. And so if you're going to use a wetland, construct a wetland, use an existing wetland, you really want to make sure that the water is actually spending time in that wetland and you have as high a residence time as you can get. Okay. And then, if you're going to build a wetland, maybe think about your irrigation management as well. Or just think about its potential for effectiveness at high flows versus low flows. And so if we look at just the functioning wetland, the percent reduction, remember, so it's positive, so, and then this is the amount of water, just don't worry about the units, just the increasing flow going into the wetland, increasing rate of flow, increasing flushing capacity, a washing, if you will, of the wetland, washing these nutrients out of it. And over these trials on the functioning wetland, the trials that had lower flow rates, the wetland was much more efficient than the trials where the flow rate was high. And so if you're going to put in a wetland and spend the trouble and the time of doing that, and you're still irrigating heavily and generating a lot of tailwater, you might want to consider integrating tailwater management in, because you're going to optimize then the effectiveness of that wetland and get a better result from both. And then looking at timing of grazing, so these layers of things that somebody could do. If we think about days since grazing, so you took you irrigate one day after the cows came out of the field, 10 days after, irrigate and the cows have been out of the field 30 days. Maybe you're looking at some kind of rotational grazing system. Above the wetland, this is what's coming off the pasture. Below the wetland, this is the effect of the wetland. It drops that value because it's very effective at filtering. Just even a 5-day rest from grazing before you irrigate will give you a 15% reduction in just the amount of E. coli coming off that field, because those fecal pads have crusted. You don't have the animal disturbance in there while you're irrigating. Some of those bacteria have died in the fecal pad. It's not a friendly environment for them. And so you can use timing of grazing. If you add to that a buffer, so you get a 15% reduction due to your grazing management, you get another 75% reduction due to a functioning buffer, and then if you add on to that the reductions you could get, say, due to effective irrigation management, you can start knocking that really high number we saw early on down to something that's acceptable, down to something you can live with. But if you're irrigating heavy, grazing while you're irrigating, and don't have some kind of filter in place, you're going to be putting numbers out that are 10 times, 100 times greater than the water quality standard. I just don't think there's any way around that. We just consistently see that from these, intensively managed pastures. So, suggestions of things you can do. I think maintaining moderate stocking rates, and Roger will talk about how do you assess what that is. And that's different for every place based on the capacity of the site to generate forage. But making sure you're trying to stay within a reasonable stocking rate for that place. If you've got room, depending on the size of the pasture, if you have livestock attractants such as off-site water, supplemental feed, shade, whatever it is, try to distribute that away from the streams as much as you can. Avoid direct in-stream fecal and urine deposition. I know if you're in a field and the stream's the only place the cattle have to drink, they're going to go down there and spend some time there. That's fine. It's just if they're camped down there day in, day out, that's when you start having some problems. Buffers and wetlands can remove these pollutants. They are one tool that's available to you. If you're going to use those on irrigated pasture in particular, I think you need to integrate them with irrigation and grazing management. And you can start with the low-hanging fruit. You can start working on your grazing management. You can start working on your irrigation management. See where that gets you. If it's not getting you where you want to be, then maybe you can look at using a buffer or a wetland. Maybe you have 3 or 4 fields that you irrigate, and it's only the last field where the tailwater actually leaves the ranch or goes onto a creek. Maybe that's the field you want to have a buffer on. You may not need it on the 3 or 4 or 5 fields where the tailwater comes off the field, simply goes onto another field. If you have a hay pasture, we're finding when you irrigate a hayfield, you irrigate a hayfield with dirty water, clean water comes off. Because the hayfield's a great sink for nutrients, sediment, and all of those things. So there's a lot of ways to use other parts of the enterprise as a way to scrub water that's coming off of an intensively managed part of the facility. And I think that's about all I have.